Let's try to understand the in-situ stress in soil. So, for soil, we have three stresses. One is known as the effective stress, which is represented by sigma prime. This is the forces transmitted from soil particles to particles, and when there is water in the soil, we will have pore pressure represented by U. So pore pressure is also known as a neutral stress. It is not created by the soil but again from the water. So it means that the pore pressure is the force induced by water filling the voids of soil, and then by adding both of these together, we will get the total stress represented by sigma, which is just the sum of effective stress and pore pressure. So we will write like this. So there are few types of question we are going to understand. So the first one will be normal situation where we have layered of soils and then with water, and it's just that will be the most basic situation. And number two, we will have seepage, which means that water moves within the soil layer, because in our first condition we assume that water is static, so there's no movement of water. But in seepage, we will consider upward and downward. And then thirdly, we will have capillary effect, for which we will discuss later because I still haven't grasped it. So first we are going to look at the normal questions. Let's go. So based on example 1, we are going to find the stresses at point A, B and C. So at first we start from point A at example 1 at point A. What are the stresses at point A? So we need to look at what's on top of point A. What's on top of point A? It's nothing, right? So anything that's at the most top layer, they will have no stress because nothing is pushing the forces downward. So at point A, sigma is 0, U is 0, then sigma prime is 0. So normally we will start from total stress and then pore pressure and then effective stress. Now at point B, sigma B equals, how do we find total stress? It is the unit weight of the layer of soil times the depth. So in this case, at B, what is above B? So it's this layer. So we take the unit weight of dry sand times the first height C1, which will be 16.5 kN cubed times Z1, 6 meter, and this will cancel. We will get 16.5 times 6, we get 99.0 kN per m cube times m. We will get the unit of kPa. Then for the pore pressure at B, now is there water on top? So the clue is it's dry sand and it's above the water table, which means that there is no water on this layer. Hence, we can say the pore pressure is 0. So the effective stress will be purely by the sand, and it's the same as the total stress of 99 kilopascal at point C. So the total stress will be now what? So C is at here. What's above C? The first layer and the second layer. So first layer we just copy from the top, dry Z1 plus, now we are considering the saturated unit weight of the saturated sand, and then the height. Then for this one we can just copy on top, and unit weight of saturated sand 19.25 times sec is 13, so the unit is the same. You get 349.25. And what's the pore pressure? Now for pore pressure, we only use the unit weight of water. So there won't be any unit weight other than water. So we have mentioned that at this dry sand layer there's no water. So only under the water table have water. So it will be 13 meter. So water times Z2. The unit weight of water is 9.81 times 13. Oops. So for those who don't remember the unit weight of water, just remember that it's rho G, then you will get 1000 times 9.81. Now the effective stress will be 349.25 minus 127.53. 1.72 kilopascal, and let's check the answer, and we are correct, the top one. Now this is fairly simple, so just a note. The note is to find total stress first. Okay, so it will be, let's just put a sum and unit weight of a layer times its depth. Secondly, the pore pressure will be sum of unit of water times the height. Then third will be the effective stress, which is total stress minus U. So we have covered that the top layer is soil, but what if the water table is at the most top? What if the water table is here? Then we take into account at this total stress here, we take into account of the starting with water times its depth. Yeah, and then yep, that's that. Now let's go to the seepage. So for seepage, we need to identify the hydraulic what is it called, hydraulic head, hydraulic gradient head. So for the hydraulic gradient, it's I, and it's the difference in head over L if seepage is downwards. Then for your pore pressure, you need to minus unit of water, Isaac. So remember, if it's downwards, then it's negative, just like a force. And if seepage is upwards, your pore pressure must add the seepage force. So remember, if upwards, then positive force. So let's go to a question with upward seepage. So we are given that E ratio, and then specific gravity. So we have water on top, and we need to find a unit weight of the soil. So with this information, we can find the saturated unit weight with the formula Gs plus E times unit weight of water over 1 plus E. So 2.67 plus 0.52, 9.81, 1 plus 0.52. This will be our unit weight. $20.588. Okay, and then since we have a upward seepage or any seepage, we need to find the hydraulic gradient I equals, so what's the head difference? It's actually this 1.5 meter. And what will be the L? The L, even though there's a point in the middle or any other condition, we take the whole length of the sample, so it will be from here to here, and L will be 2. So 0.75, it's unitless. So we can find the 3 stresses now. Start with total stress at A. What is above A? The water, and then half of the soil sample. Water and half of the soil sample. Here. So 4 A. Total stress equals to unit of water times Z1 plus saturated unit weight times actually it's just 1, so I'm going to put half of Z2. So unit weight of water 9.81 times 0.7 meter plus saturated unit weight times 1, which is 27.455 kilopascal. And then pore pressure of A is water, so only water, Z1 plus half of Z2. Then we need to plus because it's an upward seepage, right? Upward seepage, so it's positive. Unit weight of water times IZ. This Z will be, that's the same as the point A, position of point A. So we take the unit weight of water out, we factor it out, then Z1 0.7 meter plus half of Z2 1 meter plus the hydraulic gradient is 0.75 times 1 meter .035. Okay, and then the effective stress will just minus the total stress minus pore pressure. Now for point B, same thing, total stress first. So what's above of B is everything. So unit weight of water times its depth plus the whole soil sample, 20.588 2 meters. .043 kilopascal. Pore pressure this is in the water layer, then the whole layer is 2 meters plus the seepage 0.75 times 2 meter. You can factor the unit weight of water out. You will get 41.202 kilopascal, and for the effective stress, just minus 6.841, and there you have it. So let's check the answers. Yep, there's no answer. So we are almost the same. Yes. Yep. And for the capillary, I'm still trying to understand, so maybe next time. Bye bye.